Now today we discuss projection operator, one excellent topics of functional analysis. Overall, we start about definition of projection operator. Okay, so today we discuss these things. First start, let X be a linear space. X be a linear space. Okay, and Px to x and Px to x be a linear operator. Be a linear operator. Then P is said to be. Then P is said to be projection operator. Projection operator. If P square equal to P. Okay. If P square equal to P. Now we're going to some observation. Okay. Here we choose Px equal to y for all x belongs to y, for all x belongs to x. Then p square x equal to p of py, sorry, p of px. Okay, p of px, this equal to py, this equal to y, this equal to px. Okay, for all x belongs to x. This implies p square equal to p. Then this operator is called one projection operator. Okay. Next we discuss also some observation. This follows. First we show that NPV is subspace, and second RPV is subspace. We also discussed in previous class also. Then obviously here NP equal to R of I minus P and RP equal to N of I minus P. Okay. Then next if x and y x be a subspace x, then PV is subspace of x or projection of operator in x, then NP and RP be a subspace of x and P be a projection operator, then x equal to NP direct sum of RP. Okay, now we erase all these portions and going to further discussion of one result. Result is this: if P be a projection operator, then I difference P also a projection operator. If P be a projection operator, then I difference P be a projection operator. Okay. Now we're going to discussion P be a projection operator implies that P square equal to P. Now I minus P whole square equal to I minus P multiplied by I minus P equal to I minus P plus P square equal to I minus P plus P. Since P square equal to P, then this equal to I minus P. So I minus P whole square equal to I minus P. This implies that I minus P be a projection operator. Okay. If P be a projection operator, then I minus P a projection operator. Or understand this problem, we erase now this problem and further progress about this. Okay, now we're going to one important topic of projection of data. We write a theorem of proposition. We write proposition first. Okay, this propositions we write the statement with this: let X be a normed space. Let X be a normed space. Let X be a normed space. Okay, and phi x to x and phi x to x and px to x, px to x be a linear projection operator, be a linear projection operator, and in phi and rp are closed, and in phi rp are closed, then phi v closed. Okay, how we discuss this problem? We first start proof of this problem. Okay, so let xn be a sequence, let xn be a sequence in x such that xn tending to x, such that xn tending to x, and phi xn tending to y. We have to show that px equal to y. Okay, now note that rpv closed, note that rpv closed, and pxn in rp, pxn in rp with pxn converts to y. Then y belongs to rp, hence py equal to y. Okay, now npv closed, and np equal to r I minus p. The dimensionality of p equal to range of I minus p. And note that I minus p xn is in r I minus p with xn minus p xn converts to x minus y. Then we have x minus y belongs to r I minus p equal to np. Okay, now we is our portion and also going to further discussion about that. Hence phi of x minus y equal to 0, and this implies px minus py equal to 0. This implies px equal to py. This implies px equal to y. Hence PV closed. Hence PV closed. Okay. Next we're going to further discussion about that. Which one? If X be Banach space, not norm space, here we write Banach space, then 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 PV continuous. Okay. How we prove it? We erase this portion and we now prove this possibility, that this problem we prove it. Okay. How this one happen? We know that we know that we know that P be a linear operator. We know that P be a linear operator. P be a linear operator with domain dp on a Banach space X, on a Banach space X with dp be closed, with dp be closed, then P is a closed linear operator. Then P be a closed linear operator. So P be a closed linear operator and also X be complete. X be complete. Banach space means complete. Then any Cauchy sequence converging to X. This means P be a bounded operator. Okay. Hence P be a linear bounded operator. So PV continuous. Understand? Next we discuss about another problem or another example of projection operator. Okay. X equal to r square and pxy equal to x0 for all xy belongs to r square. Then p square xy equal to p of pxy, then p of x0, this equal to x0, this equal to p of xy. Hence PVA projection operator. Next we discuss about these things. If x belongs to L2, that means p of x1 x2 dot xn equal to x1 x2 0 0 0. If we construct this phi of x1 x2 dot 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 x3 dot dot dot, okay, in this way, then what we get, this one equal to x1 x2 0 0 dot dot dot. If this operator, if this operator and x be L2 space, then what happened, then p square of x1 x2 x3 dot 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 equal to phi of x1 x2 x3 dot 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 equal to p of x1 x2 0 0 dot dot dot. This implies that x1 x2 0 0 dot dot dot, then this one equal to, this implies that p square equal to p. Okay, so PVA projection operator, here also PVA projection operator, PVA projection operator. Okay, so we discussed two examples, x equal to R2, x equal to L2, and we defined some P, and this one is a projection operator. We gives one important propositions and two, also two example, and also the definition of projection operator and some observation about projection operator. So we now further proceed. We also discuss one important theorem. We all known about that. This one is Hahn-Banach theorem, and we proceed continuously. That means we proceed uh, in the way of Hahn-Banach theorem. But first we discuss some important definition, okay, and some important results which are basic tools to prove Hahn-Banach theorem. Okay, so today we discuss sublinear functional. Where is this portion now? Let X be a linear space over K. Let X be a linear space over K, and Px2R be functional, and Px2R be a functional. Then P is said to be, then P is said to be sublinear. Then P is said to be sublinear. Okay. Then P be a sublinear if if first one, if P be subadditive, if P be subadditive, that is Px plus y less than equal to Px plus Py. Okay, for all x y belongs to x. Okay, next we're going to sublinear functional. Then first, P is said to be sublinear if P be subadditive. Then Px plus y less than equal to Px plus Py. And number two, Pb positive homogeneous. Pb positive homogeneous. Okay, then P of, that is P of alpha x equal to alpha of Px. Okay, where alpha greater than 0 and for all x belongs to x. Okay, now we're going to another portions. Every norm is subadditive. In a linear space, every norm is subadditive. Okay, because we know about that norm of x plus y less than equal to norm x plus norm y, and norm of alpha x equal to alpha norm x. Okay, here mod of alpha is better. Okay, if alpha greater than 0, then this one happen. So this implies that in a linear space, in a linear space, in a linear space, every norm is subadditive. Every norm is subadditive. Every norm is subadditive. Okay, next we discuss about some partial order relation. This one example of subadditive functional. Okay, next we also erase this portion and going to further discussion about partial order relation. Now partial order relation, okay, or partial order set. Partial order set. Let x be a set. Let x be a set. Then a relation less than equal to is said to be a partial order relation. A partial order relation if first one, this be reflexive, and this be antisymmetric, and this be transitive. Okay, then this relation is called a partial order relation. If this be reflexive, this be antisymmetric, and this be transitive. Okay, reflexive means we know about that x less than x holds. Okay, and antisymmetric means x related to y and y related to y holds implies that x equal to y. Okay, next transitive means x related to y, y related to z holds implies x related to z holds. Then x related this relation is called partial order relation, ordered ordered set. Okay, and this relation is called partial order relation, and this set is called partial order set. Okay, now here we also want also one definition. A and V be comparable if either A less than equal to B or B less than equal to A hold. Chain linearly or totally ordered set. Okay, linearly or totally ordered set. Let x less than be opposite and x subset of x. Then S is called chain if any two elements of S are comparable. Then S is called a chain. Then S is called a chain if any two elements of S are comparable. If any two elements of S are comparable. Okay. Now we're going to one important lemma, which is Zorn's lemma. Okay, we use this for sums now. Let x less than equal to be a poset such that every chain of x such that every chain of x has an upper bound. Then x has and maximal element, then X has an maximal element, maximal element. Okay, now we're going to all descriptions of John's lemma and other things. That means some projection operator, related theorem or related proposition, example, sublinear functional, definition of example of sublinear functional, and partial order set, comparable of two elements in partial order set, chain and totally bounded or linearly bound ordered set, totally ordered or linearly ordered set. Next, John's lemma. Okay, we also discuss every that means every topics in a suitable way. So today we stop here.